Okay, so the next thing we want to do is we're going to start to work with catenary curves. And catenary curves are a very, I think, clear and direct way for us to begin to implement using particles and springs in a way that we can kind of understand what we're going to get when we work with them, right? So catenary curves, right, would look something like this if this is a sketch of what we're about to produce, right? And a catenary curve is just the shape that is assumed under its own self-weight, right? So typically we can talk about catenary curves as being understood as chains, and that's a really direct way for us to kind of wrap our head around what it is, right? If we have a chain with a collection of links, and each one of the ends of the chain is anchored to a location in space, right? The additional length that is allowed by these two anchor positions allows the chain to fall into a naturally curved shape, right, where all the forces are equaling out throughout the chain, right? So what's nice this is a series of diagrams by Heino Engel, right? If we think about a chain, right, and the curve that it produces, it's going to be in complete tension if we hang it under gravity, right? And again, this is a curve that is produced under its own self-weight. And if we invert that, right, then the resulting arch is still a catenary curve, but is in complete compression. Now, for structures and architecture, that's really a useful trick, right, that we can invert. It's called the principal of inversion. We can invert a catenary curve that's falling under its own self-weight such that in its opposite shape, it is under complete compression, right? So there's no tension forces inside the shape, and that's a very efficient shape to use structurally. All right, so let's go ahead and build out a catenary curve, and we're going to still use the same kind of base curve here. That's going to be our starting point. And to get a sneak peek of what we're going to be doing, you could go ahead and open up the 1-2A catenary by chain file. Right, and this is as many objects as we're going to produce. A lot of this should look pretty similar, right? Where we have our physics engine object over here with our controls and our merge objects that allow us to collect all of our forces and anchors. All right, so just as we did before, let's go ahead and save as. That's my underscore working file. And let's go ahead and delete back to the input curve. So I'll leave my input curve because we know how to produce that. And that's where we'll start from for this file. All right, so let's go ahead and bring our curve into Grasshopper by right-clicking. Say set one curve. All right. And now what we're going to do is we're going to assume that this is a chain, right? So if I were to, just as an example, divide this into a series of points, right? We can think of each one of these segments as a chain link, right? So at its rest length, this is how long the chain is, right? Based on the length of this curve. So if I analyze its length, it says 61 meters. So the idea here is that it's not going to change from 61 meters while we're simulating it, right? So I can get rid of all these points, and we can start to work with that idea in Grasshopper, right? And what we're going to do is first take the curve and divide it into a series of points so that we can see, first define how long our chain links are in terms of how many there are, and then how long each one is. So let's go to the curve tab. We're going to divide our curve just as we did before. Divide curve. All right, and this is going to be our input, and we need a slider for our number of segments. So let's use our same shortcut by double-clicking the canvas. We'll say 1 less than 20 less than 50. All right, so now I have 20 segments. This is my num div, just as we did before. Okay, now each one of these should be equally spaced in terms of their distance along the curve. So what we've done is we've created a simple chain where each length of chain is the same. All right? So in order for this to fall in a catenary shape, we actually have to say that the overall length in terms of where the anchors are, the two endpoints, if we slide them closer to each other, that should allow the chain to fall further. And vice versa, if we stretch them farther apart to the ends, the chain shouldn't fall much more than the shape that we have right now. All right, so in order to move the endpoint of this chain along the curve here, we're going to take a subcurve of the original curve, and that way the endpoint of the subcurve will be moving along this edge here. All right, so what we're going to do is we're going to go to the Curve Spline tab. We're going to grab the subcurve object. All right, and this asks for the curve that we want to extract a subdomain from. So we'll connect our input curve into it. And D is the subdomain to extract. So let's assume that we want to start at the beginning of a curve, 0, and if we assume the end of the curve is at t value 1, right, we can move along this curve with a simple slider that's bound between 0 and 1, right? So we're going to move the space of the curve by a default slider that I'm going to get from params input. This is between 0 and 1 by default. So I'm going to label this T and connect it to D. And at the same time, if I want to ensure that my curve is understood as 0 to 1, I'm going to reparameterize it. So I'm going to right-click C and say reparameterize. So if I turn the preview off of everything, you'll see here that I have a curve that's going this far along my original curve. That's my subcurve. Right? And I can shift how long that curve is. Perfect. So with that subcurve, I want it to be understood as a collection of chain links as well. So I'm going to copy and paste my divide and use the same object and replace the C input with the curve so that now I have this set of chain links, right? Okay, so the next step is that we want to say that the segments in between these points are going to be springs, and then the endpoints of this curve are going to be our anchors, right? And that way we should have a the ability to calculate a catenary curve if we place it under gravity, right? Give a little line here to indicate gravity. There we go. All right. So we have our points, which will become our particles. We'll have our springs, which are going to come from these line segments. And our force will come from gravity, and we'll bind the chain to the endpoints here and here. Okay. So let's start by defining our springs, right? And we need to get segments. So if you have a suggestion on how we can go from points or t values to segments based on this division strategy, go ahead and drop it into the question window and give us a suggestion. I'll give you a hint. It's going to be under curve division. All right, you got it. It's shatter, right? We're going to go to division, shatter, and we're going to use from our subcurve and the t values coming out of the division, that's going to determine the shatter locations. So we're left with a series of planar curves here. So each one of those segments. All right? Perfect. Now we're going to do the exact same thing for the original curve. So I'm going to copy and paste this use my original input curve and my division point t values here. So now I have the segments as they were originally, and that's going to give me their rest length. And this is going to give me the actual spring line segment. All right, so I'm going to save this, and let's go ahead and start to create all of our physical geometry. And these are our springs, etc. So if we go to the Kangaroo tab, let's start with the springs. Those were found under the Forces subtab. All right, so our connection is going to be the line segments that we have here. And the rest length is going to come from the original length, right? Because if we say rest length here, if we use the length for these shattered segments, that's going to be changing as we go, right? The idea here is that we're working with a chain as if it exists in the physical world, right? Where the links of the chain do not change as we change our positions of our anchor points, right? So we're going to find the curve length from curve analysis of the shattered segments up here, and that's going to go into our rest length object. All right. So now we have the rest length and the connections defined. So our springs should be good to go. All right.